Okay, so let's look at the heat equation in cylindrical coordinates. Now remember, in cylindrical coordinates, in general, you assume that the temperature U depends on the space coordinates, so rho, phi, and the z, the Cartesian coordinates, and then the time t. And remember that if you were to sketch these coordinates, basically for a typical point, this is basically the rho, this will be the phi, basically these are the polar coordinates. Say this is the x-axis, this is the y-axis, and then the z-coordinate is just the Cartesian coordinate. For simplicity, remember, if we talk about the solving a boundary value problem in this class, we make assumptions so that the temperature depends on two variables only. Now, you remember previously we talked about a steady state temperature in which the temperature depended on rho and phi only. You know, the equation that led to the Cauchy-Euler equation. Now I want to solve a heat equation in cylindrical coordinates, so I want to actually have the temperature still depending on time, but as simplifying assumptions, we assume that the temperature doesn't depend on phi and z. So if you want to imagine an object with such properties, imagine basically a cylinder in which the temperature only propagates along the radius of the horizontal section. So it doesn't depend on z, doesn't depend on phi as you go around the horizontal section. It just depends on the horizontal radius of the horizontal section, the radius of the horizontal section. I suppose imagine, for example, you have an infinite wire or a long wire in which you have basically the inner core here heated up, or the outside cover of the wire allowing the temperature to flow from the inside to the outside and back and forth, again, just along the radius. So in these assumptions, you could assume that the temperature depends only on rho, the radius, and the time t. And then the heat equation, and at this point, take a look at the Laplacian in cylindrical coordinates. The heat equation would be U partial t, some conduction term a squared, and then U partial rho twice, plus 1 over rho U partial rho. Okay, so this would be the Laplacian in cylindrical coordinates, assuming that there is no dependence on phi and z. Okay, so all partial derivatives with respect to phi and z will be 0. Let's forget for a moment about boundary conditions. So obviously, you need to specify a domain for rho. So suppose that rho is between 0 and c, right? The radius of the object. But let's forget about the other boundary conditions for a moment, and let's see how the PDE separates into two ordinary differential equations if you do separation of variables. So as with all problems involving separation of variables, you assume your function is a product of functions in rho and little t. Plug it into the PDE, so we have r of rho t prime of t equals a squared r double prime of rho big T of little t plus 1 over rho r prime of rho big T. On the next step, we're not going to write rho in t because we know already that big R depends on rho and big T depends on little t. And let's do some algebra. So here we can factor big T. And now separate. So divide by a squared t and divide by r as well. Then introduce a separation constant. So we have t prime over a squared t equals r double prime plus 1 over rho r prime divided by r, and then the separation constant, which is going to be positive, you'll see later, and we can just write it as minus lambda. Lambda will be positive just for convenience, as you'll see later on. So this is how the separation looks like. And on the next page, let's write down the two equations side by side. So notice here, I'm going to multiply by r and move everything to the left side. So let's actually do it here on the same page. So the equation in t is going to be t prime plus lambda a squared t equals 0. No surprise here. I mean, it's something you encountered before, the t equation. But the big surprise and the whole point of this chapter is the Sturm-Liouville problem, which comes up when you write the equation for r. So r double prime plus 1 over rho r prime equals minus lambda r. And let's move lambda r on the left side and then multiply by rho both sides just to clear it from here. So so we have r double prime plus 1 over rho r prime plus lambda r equals 0. And if I multiply by rho both sides just to eliminate this parenthesis, we're going to have rho r double prime plus r prime plus lambda rho squared. Plus lambda rho, I'm sorry. Lambda rho big R equals 0. Okay, so let's write it down on the second page. I mean, on the third page, I suppose, at this point. So let's write it down on the, actually, I forgot the count, but let's write it down on the next page. So in this method, right, the Sturm-Liouville problem will be coming from the ODE rho r double prime plus r prime plus lambda rho r equals 0. So this may not seem like a big deal, and you might actually think of it in terms of the Cauchy-Euler equation, but it's not the Cauchy-Euler equation. Notice if I actually multiply by rho on both sides just to see if it's of a Cauchy-Euler type, because remember in the Cauchy-Euler type, the exponent of rho should be the same as the order of the derivative. So if I do that, then this is rho squared r double prime plus rho r prime plus lambda rho squared r equals 0. So the reason sometimes this is confused with the Cauchy-Euler type is because the first two terms look like the Cauchy-Euler type, but it's not Cauchy-Euler. The Cauchy-Euler would be of the form a rho squared r double prime plus b rho r prime plus c r equals 0. There wouldn't be any rho, any coefficient in terms of rho multiplied by r. So this equation is not Cauchy-Euler, right? So this is the Cauchy-Euler. So this is Cauchy-Euler type. What you have in the actual problem, it's not Cauchy-Euler. And if you actually enter this equation in some computer algebra system, you will see that actually the solutions are given in terms of the so-called Bessel functions. So I'm going to add a part here with a little screenshot from running this type of equation in Maple. But suffices to say that this is basically one type of the so-called Bessel equation. So Bessel ordinary differential equation. So there are several types of Bessel ordinary differential equations, and this is essentially one of them that appears in the context of the heat equation of in cylindrical coordinates. So let me end up with the general definition of a Bessel equation and add a remark on how this connects to this type of problem that appears in the separation of variables context. And then from this point on, we're going to just study the properties of Bessel functions, which are solutions to the Bessel equations. So as a definition, we say that a Bessel equation of order n is, so a Bessel equation of order n is the following second order homogeneous ODE. So x squared y double prime plus x y prime plus x squared minus n squared y equals 0, where n can be 0, 1, 2, 3, and so on. So Bessel equations are a family of second order homogeneous differential equations. And what came up before in the process of solving that boundary value problem, that heat equation, was simply one type of Bessel equation. Now, there are more than these ones. I mean, there's a slightly more general definition of Bessel equation in which this coefficient here, this n, doesn't have to be integer like we mentioned here. But we're going to focus only on these types of Bessel equations. So once again, a Bessel equation is nothing but a second order homogeneous ODE in this specific format. Okay, so the dependent variable in this notation is y of x. You have the coefficient x squared or y double prime, xy prime, just like in the Cauchy-Euler type, but this last term is different, is given in this form, x squared minus n squared times y. So that's a standard form of a Bessel equation of order n. You may wonder why it's in the standard form. Well, because the solution of it has a very specific format that can be studied as a single entity if you want. And I want to point out, and that's another important remark at this point, what we had before in the process of solving that heat equation. So when we had rho squared r double prime plus rho r prime plus lambda rho squared r equals 0, you will see later that this is basically equivalent, and we're going to show that in the next lecture. This is equivalent to a Bessel equation of order 0. So in other words, when n is equal to 0, the Bessel, when n is equal to 0, the Bessel ODE has this specific format. And if x is not equal to 0, if x is positive, as it is the case in many of these applications, you could divide by x both sides, and that equation can be written in this format. So when n equals 0, Bessel equation of order 0, you could actually cancel a factor of x if x is positive or not equal to 0. And then this is another more compact form of the Bessel equation. So let's summarize what we had so far as a preliminary topic. There are other Sturm-Liouville problems besides the one we encountered so far, leading to either eigenfunctions besides sine and cosine. Those eigenfunctions, as long as they are orthogonal with some weight function, then one can still proceed with the method of separation of variables. And then finally, the last part of today's class, notice that in the context of the heat equation in the cylindrical coordinates, when you do separation of variables, one ends up with a second order ODE of a different type that we encountered before. And this one happens to be equivalent, as you'll see later, to a so-called Bessel equation of order 0. More generally, a Bessel equation of order n will have this format. So on the next lecture, we're going to study, well, first of all, we're going to show that indeed this is equivalent to a Bessel equation of order 0, because notice there is this pesky lambda here that makes it a little bit different than what we have in the general theorem here, in general definition. So we're going to show that this is indeed equivalent to a Bessel equation of order 0. And then from that point on, we're going to study properties of solutions of these Bessel functions, which are solutions to the Bessel ODE. And that's it for today.